In all types of machinery, forces are transmitted from one component to the other, such as from a belt to a pulley, from a brake drum to a brake shoe, from a gear to a shaft. In the design of machine mechanisms, it is necessary to know the magnitudes as well as the directions of forces transmitted from the input to the output. The analysis helps in selecting proper sizes of the machine components to withstand the stresses developed in them. If proper sizes are not selected, the components may fail during the machine operation. If the components of a machine accelerate, inertia forces are produced due to their masses. However, if the magnitude of these forces are small compared to the externally applied loads, they can be neglected while analyzing the mechanism. Such an analysis is known as static force analysis. For example, in lifting cranes, the bucket load and the static weight loads may be quite high relative to any dynamic loads due to the accelerating masses, and thus static force analysis is justified. Next one, dynamic force analysis. When the inertia effect due to the mass of the components is also considered, it is called dynamic force analysis. Applied forces. Forces acting on the system of bodies from outside the system are called applied forces. When two or more bodies are connected to form a group or system, the action and reaction forces between any two of the connected bodies are called constraint forces. Example, a block resting on floor, W is applied force and R is constraint force. In this example, applied force is mg, constraint force is T, which is mg by 2 cos theta. In this example, applied force is P, constraint forces are Ra and Rb, which are equal to P by 2. For this cantilever, the applied force is P, applied moment is P into length L, constraint force is Ra, which is equal to P, constraint moment is M, which is equal to P into L. In this example, the applied force is small p into capital A, which is a wind force. Constraint forces are Ra and Rb, which are equal to small p into capital A divided by 2. In this example, applied force is the force caused by thermal stress P, and constraint forces are Ra and Rb, which are acting in opposite directions. In this example, the applied force is P, which is spring force K into delta, where K is stiffness of the spring and delta is the deflection of the spring, and constraint forces are Ra and Rb. In this example, the applied torque is the tightening torque P into L in clockwise direction, and the constraint moment is M, which is equal to P into L in opposite direction. Conditions for equilibrium. A body is in static equilibrium if it remains in its state of rest or motion. In static equilibrium, the vector sum of all forces acting upon it is 0. The vector sum of all moments of all forces acting about an arbitrary axis is 0. Mathematically, sigma f is equal to 0 and sigma m is equal to 0. Equilibrium of two force members. A member under the action of two forces will be in equilibrium if the two forces are having the same magnitude and the forces act along the same line and the forces are in opposite direction. Equilibrium of three force members. A member under the action of three forces will be in equilibrium if the resultant of the three forces is equal to 0, and the second condition is the lines of action of the forces intersects at a single point which is called the point of concurrency. Equilibrium of two forces and a torque. A member under the action of two forces and an applied torque will be in equilibrium if the forces are equal in magnitude, parallel in direction and opposite in sense, and the second condition is the forces form a couple which is equal and opposite to the applied torque. Equilibrium of four force member. The equilibrium of a member under the action of four forces will be checked by reducing the number of forces acting on a body to 2 or 3. Principle of superposition. The principle of superposition states that if number of forces act on a system, the net effect on the system is equal to the sum of the individual effects of the forces taken one at a time. Force convention. The force exerted by the member I on the member J is represented by Fij. Similarly, the force exerted by the member J on the member I is represented by Fji. Fij is equal to minus Fji. The magnitude of Fij and Fji is same, but the direction is opposite. Free body diagram. A free body diagram is the diagram of a link which is isolated from the mechanism, showing all the active and reactive forces acting on the link. The example, a block on a ramp, it is left side, and the free body diagram is shown in the right hand side. Now let us do some problems in static force analysis. Problem number 1. In this problem, a slider crank mechanism is given. Force F is acting on link number 4 at B. OA, AB dimensions are given. We have to find out what is the input torque on the link OA for static equilibrium. Let us solve the problem. First of all, draw the configuration diagram, and from the configuration diagram find out all the angles and the sides which are unknown by using sine rule or directly from the diagram by measuring. First, let us draw the free body diagram of link number 4 and find out F34. So this is the free body diagram by using sigma Fx is equal to 0 minus 2 plus F34 cos 11.09 is equal to 0. From that, F3 is equal to 2.04 kilonewton. Now from the free body diagram of link number 2, we can easily find out the torque acting on link number 2. So torque is equal F32 into H, that is equal 153 Newton meter in clockwise direction, which is the answer. Now problem number 2, which is a 4-bar mechanism. So in this 4-bar mechanism, the dimensions of all the links are given and one angle is also given. On the link number 4, a force 80 Newton is acting at an angle of 150 degrees. We have to find out T2. Now let us proceed from the link number 4, draw the free body diagram of link number 4, and sigma MD is equal to 0. You will get F34 into 750 sine 50.5 is equal to 80 into 350 cos 12. From that, F34 will be equal to 47.32 Newton. Now let us take free body diagram of link 2. So on link 2, torque 2 is acting and F32 which is equal to F34 is acting. By taking moment equation at point A, we will get the value of T2, which is equal to F32 into the arm distance. So we will get T2 18.72 Newton meter clockwise. Problem number 3. It is also a 4-link mechanism. In this problem, T3, T4 which are acting on link number 3 and link number 4 are given. We have to find out T2 which is acting on link number 2. This problem can be solved by using law of superposition. First of all, we neglect T3 by considering T4 and find out T2A. Next, we neglect T4 and considering T3, we will find out T2B. Adding those two, you will get final value. So, first of all, take the free body diagram of link number 4 and find out F34. And secondly, take the free body diagram of link number 2 and find out the torque acting on link number 2, which is T2A. This is the case number 1. In the case number 2, neglect T4. Take the free body diagram of link number 3. Find out F23 first. F23 is equal to 44.8. Next, take the free body diagram of link number 2. Here at point B, F32 is acting in the opposite direction of F23 and calculate the value of T2B. Now, by using law of superposition, T2 is equal to T2A plus T2B, which is equal to 16.18 Newton in counterclockwise direction. Thank you for watching the video. Please subscribe the channel and share the videos to your friends. Thank you.